Okay, let's take a look at Unit 2, 2.5. We're looking at movements in space here. The last unit, concept for this unit. And if you...
wireless headphones. That'll be $200.
I'll use my...
If you quickly take a look at the Explore here, you'll notice that there's just one Explore page, right? But it's a long Explore page. I'm just going to give you guys a heads up on that, okay? So let's take a look at and write down the essential question: how are movements of objects in space categorized? Right? Planets move, moons, the satellites, natural and artificial, they move. Asteroids, comets, galaxies, they all move. So how do we organize these? Write down what you think. Okay, hopefully you've had a chance to write that down. So the very first section, we've made this Roman numeral 1, describes planetary motion. And you'll want to write down all this information that I have here. Things such as orbiting. We orbit the sun. We are smaller than the sun. The moon orbits Earth. The moon is smaller than Earth. So smaller objects moving around larger objects. Terms such as revolutions, they mark a complete, right? A complete orbit around the star. So our revolution, where we orbit around the sun, a revolution for us is 365.25 days. How do you account for the quarter day? Well, you have a leap year every 4 years, right? We're just kind of making sure that you guys have all the information there, okay? Now, you're going to come across this other idea here. Planets, they can travel in orbits one or two directions. There can be direct or retrograde movement. We are trying to get this thing to move. There you go. You can see here in red that we discuss retrograde movement. You often see it in smaller objects such as moons. That's where they move in a direction opposite of Earth's direction. We would call that retrograde movement, okay? Orbits of planets can change. Okay. How? Changes to orbits can occur due to gravitational effects from other objects or collisions with other objects. It'd have to be a pretty large collision to make a planet change its orbit, right? But, you know, it can happen. And certainly for smaller items, if you have an asteroid that's orbiting around your planet and it collides with something, it certainly could reverse its direction or just go off course entirely, right? Number 6 here, even though objects pull on Earth on each other, they don't collide with each other because of their inertia. Okay, that's a tendency for an object to remain in the motion that it's moving. When inertia and gravity, this is going to be small a, when inertia and gravity are perfectly balanced, orbits can develop. Okay, so you can see in this picture here, we've got an example of a planet in blue, and its inertia would want it to go straight forward, but the inertia is balanced with the force of gravity from the star that it's orbiting. And so what results is in an orbit. It's because of perfectly balanced gravity and inertia. Okay. And I think we mentioned this, when smaller objects collide with planets, they generally result in a crater. No, we didn't mention this, rather than changing the orbit. Okay, so Earth has got plenty of craters on it as a result of things colliding with us. The largest one being Chicxulub or Chicxulub in Mexico, which they thought was maybe the dinosaur killing asteroid event on Earth, right? Sometimes you can have asteroid collisions with other asteroids. There's the Kuiper Belt. It's believed to be a fragmented planet that never really formed, and that exists between Mars and Jupiter. And sometimes those asteroids can collide with each other and be knocked out of their orbit, and they can start to come into inner space closer to us, sometimes resulting in things like comets. Now, you and I and our moon, our planet, and our sun, we're not the only things affected by gravity. Galaxies are also affected by gravity. At the center of every gravity is a black hole, right? A massive black hole. And galaxies can attract other galaxies, and we call these galactic groups, right? Just making sure you have all that, okay? And you can kind of see how we're just tracking here with your notes, right? Okay, so the gravitational pull, number 8, of objects on each other can alter the shape of their respective orbits and movements. Okay, so in this example here, we have Earth, we have the moon. Interestingly enough, the moon you would think is orbiting around Earth, specifically the center of mass of the Earth, but you've recently learned how to calculate centers of mass. And for the Earth-Moon system, the center of mass is actually off center. It's just below the surface of Earth. And so between Earth and the moon, there's a small wobble effect as the moon revolves around that point, and the Earth is trying to revolve around that point as well. And so you get this wobble, and this is what they call the barycenter. Okay, the barycenter is the center of mass for the Earth and Moon system. So the moon is orbiting that point, as is the Earth. Okay. This wobble effect can be seen with other objects such as the Sun and Jupiter. The center of mass for Sun and Jupiter is just above the surface of the Sun. So both orbit that point, causing the... Maybe I'm going to do this. I'm going to drop that down. I'm going to enlarge this, and hopefully that'll make this a little bit easier for our viewing, okay? Let's do that. So both orbit that point, causing the sun to wobble. Astronomers use wobbling of stars as a clue that there might be planets. Yeah, we take our big telescopes, we aim them at stars, and if we see a wobbling effect, we have to suspect that maybe that wobble is caused by some other massive objects and their centers of mass affecting each other. That's how we aim our telescopes and look for different planets. Okay, Roman numeral 2, we got to talk about Kepler, Johannes Kepler, and his laws of planetary motion. 17th century, so this was stuff he developed in the 1600s. He said that we are wrong to think that planets orbit their stars in a nice circular pattern. More realistically, he said, they're elliptical orbits. And in every elliptical orbit, you're going to have eccentricity, that is a degree to how much it's a perfect circle or a straight line. Zeros are perfect circles, ones are straight lines. Most planets are going to be closer to the zero value, so they're going to have this ellipse. And in an ellipse, you have two foci, two focal points. The sun is always going to be located at one of those foci. Okay, so that's Kepler's first law. Kepler's second law is interesting as well. Basically, he said that, and you can see these shaded areas in this picture. Those areas are the exact same amount of area. So, as a planet is far away from the star, it's going to be sweeping at a slower speed. So, it moves slowly compared to when it's closer to the star. You can see that between 5 and 6, it's covered a bigger distance of its orbit just to maintain that same amount of area. So that means it has to travel faster to cover the same amount of area. That's Kepler's second law. Okay. Um, no matter where it is traveling, and it's going to cover the same amount of time, but it must slow down or speed up in order to achieve this. Okay. And then you have Kepler's third law. This holds true for both circular and elliptical orbits. Just a little side note, FYI. It says that the square of a planet's orbital period, defined as 1 year for Earth, right? An orbital period is how long it takes to revolve to orbit its star. This is directly proportional to the cube of its average distance from the sun. So there is a relationship between the time it takes to go around and the distance. Okay. And if we take a look at that law and put it into formulations, you can see in black here that the orbital period, t representing the orbital period, is going to be squared, is equal to a cubed. The distance is the letter a cubed. In red, you have this would be like a constant of proportionality. In your book and text, they'll omit that just to let you focus on the real heart of this formula. That is that t squared equals a cubed. Roman numeral 3, laws of gravitation. We've talked about that, right? Refer to your past notes. A lot of this stuff you already know. Objects rotate around their axis. Earth has an axis that tilts at 23.5 degrees, and it takes us 24 hours to rotate on that axis. There's a term called precession, wobbling in a planet's rotation due to the rotational axis changing over time. So that axis can change from time to time. Hey guys, I'm recording, so if you can take that down. Okay. One of Earth's ice ages could have resulted from this. Okay, so and take a look at that. Precession seems to take about 26,000 years. Precession varies over time, which results in another wobble referred to as nutation. So make a note of that. Earth's nutation due to gravitational force of the sun and the gravitational force of the moon lasts about 18.6 years. Okay, so and these are things I'm going to probably talk to you guys about in your smaller lectures in class. Satellites are anything that's small that orbits around a larger object. It can be natural. Things like the moon are called satellites, but humans make satellites as well, artificial. Sometimes these satellites can be tidally locked. As you can see here, the moon is tidally locked to the Earth. That means that the face of the moon is always going to be facing the Earth. We never get to see the backside. The only way that can happen is if the rotation of the moon is exactly the same speed as its orbital speed. You're going to talk about Earth's tides as well, how water bulges, and that's why when you go to the beach, you have high and low tides. These are affected by Earth's gravity, by the moon's gravity, and by the sun's gravity. Okay. Roman numeral 7. You're going to hear these things about perihelion and aphelion. As a planet orbits around the sun, sometimes it's near the sun, we call that perihelion. Sometimes it's far away from the sun, we call that aphelion. Okay. When you're furthest away, the force of gravity from the sun is at the weakest points. When you're closest, and for Earth, we're closest to the sun in January, perihelion, that is going to be the strongest. Roman numeral 8, equinoxes and solstice. So You know that when we're furthest away, if in the northern hemisphere, that's our winter. And when we're closest to the sun, the northern hemisphere, that's where we're at, we experience our summer. Halfway between those points, when the sun is warming up both the northern and the southern hemispheres equally, we call those your equinox, meaning equal. You have a fall equinox when you're going from summer to winter, and you have a spring equinox when you're going from winter back to summer. Roman numeral 9, solstices. Okay, solstices refer to how high the sun is.
Good morning, Bruin.
Inside
Please
the
stand for the Pledge of Allegiance. Staff and students who are walking on campus, please stop and turn towards the flag.
So
Ready?
solstice
Begin.
refers
I
to
pledge
how
allegiance
high
to the flag of the
the
United States
the
of
sun
America,
is inside
and to the republic for which
when you
it
look up in the
stands,
sky.
one nation, under God,
You can see
indivisible,
that you have a
with
northern
liberty and justice
solstice.
for all.
This
Your
is
own
our
announcement
longest
for
day.
February 1st,
It goes from
2024.
January 20th or 21st. You also have a southern solstice, and that occurs December 21st or 22nd. Your southern solstice is where the sun is going to be riding low in the sky. Your northern solstice is going to be riding high. Okay, summer solstice versus winter solstice. Okay. Roman numeral 10, and we'll go and review this again. You have moon phases every 28 days. The moon is going to orbit around the sun, and that accounts for how visible the moon is in our sky. All right. And then, of course, you have your eclipses. You have your lunar eclipses. You have your solar eclipses. Okay. Whenever the moon is in between the sun and the earth, it's going to produce a shadow on the earth. Okay. And you can see that there's what we call the dark shadow, which is called the umbra, and you have the lighter, whiter shadow, which is called the penumbra. And these would be examples of solar eclipses here, and you have three types of solar eclipses. You have your total solar, partial solar, and you have your annular solar eclipse. You also have your lunar eclipses. Okay. In this case, the moon is experiencing the eclipse because Earth is passing between it and the sun. You still have these ideas of umbral shadows. And you also have to be aware of the fact that lunar eclipses don't occur every month because they actually are not in a perfect line with the sun and the moon orbiting. They occur at a 5-degree tilt, and that's why we don't always get to see a perfect lunar eclipse every month. Okay, so that was a lot of material. You're going to have to go ahead and read through that, and we'll be having these little mini lectures inside class as well to discuss that information. I hope that was useful. And let's see if we can just drag this stuff all back off to the side here. And let's see if we can end this recording here, okay?